Alright guys, in this video I'm going to go through neutralization reactions. These calculations involve reacting an acid with a base and then working out the pH of the remaining mixture. Firstly, you need to find out what's in excess and by how much. If you have excess strong acid, you simply use minus log H+. If you have excess weak acid, you use the Ka expression. And if you have excess base, you use the Kw expression. Alright, so I'm going to walk through an example just so you guys understand what I mean by that. And then I'm going to give you guys one to try out yourselves. So firstly, when I have these, I normally write down the equation. So I've got hydrochloric acid reacting with sodium hydroxide. So I'm going to write down the equation for that, and I get... And now I like to do a table. Now it's a bit like the ice table. However, this reaction doesn't go to equilibrium, right? It actually finishes. So instead of writing down equilibrium, you can just do you can write final moles instead. So initial, change in moles, and final moles. Now for our initial moles of sodium hydroxide, we have 35 centimeters cubed. And if we want to convert that to decimeters, we divide it by 1,000. I'm going to times it by the concentration, and I get the moles as 0.01925. And I'm going to do the same for hydrochloric acid so that I get... Now these are our initial moles before they actually react. So I'm going to write that down in the I section. Now these react in a 1-to-1 molar ratio. So because of that, you know that since this is the limiting reactant, all of this is going to get used up, okay, the acid. So essentially, you do take away 7.5 times 10 to the minus 3 for both of them. And the reason why you subtract this is because you know by the end of the reaction, you should have 0 moles of HCl because it's the limiting reactant. And these are your final moles. Now, you know that sodium hydroxide dissociates in a 1-to-1 molar ratio. So this is the equation of the dissociation. So if you have this many moles of sodium hydroxide, you have this many moles of hydroxide ions. Alright, here we have the moles of hydroxide ions, but we need the concentration of hydroxide ions for the Kw expression. So we do moles divided by volume to work out concentration. So for moles we use this value, and for the volume we do 35 plus 15 to work out the total volume. And we get this. Alright, so this is our value. Once again, this volume comes from the total volume. And I've divided it by 1,000 or times it by 10 to the minus 3 to convert it into decimeters cubed. So now we have moles per decimeter. Now we can sub this into the Kw expression to work out our H plus concentration. Alright, so for our Kw expression, I subbed in the value of Kw at room temperature because when they haven't stated the value, you just use 10 to the minus 14. And now I've got H plus concentration. I can do pH equals minus log H plus to work out pH, and I get 13.37. Alright, here's an example for you guys to try. Pause the video, try it yourselves, and play to see the working out. Okay, once again I'm going to write down the equation of the reaction. So I get, and I'm going to draw my table. Now I'm going to work out the initial moles of the hydrochloric acid and the sodium hydroxide. Alright, in this instance, our sodium hydroxide is the limiting reactant. So we know that in the end we have 0 moles of sodium hydroxide. Therefore we take away 0.0195 from both sides because all of the sodium hydroxide is used up. Alright, now we know we have this many moles of hydrochloric acid. Now this dissociates in a 1-to-1 molar ratio. So if we have this many moles of hydrochloric acid, we know that we also have that many moles of H plus ions. Now to work out H plus concentration, we do moles divided by volume. Alright, so I got the 75 value from adding 45 and 30. And I times it by 10 to the minus 3 to get in terms of decimeters. And my answer is... Alright, and now to work out pH, I'm going to minus log this, and I get 0.47. Alright, so this is the final one we're going to go through. So once again, I'm going to... Oh, actually, I've already got the equation written down. So I'm just going to write down the ICF table. Now I'm going to write down the initial moles. So we have... Alright, from this I can tell that my sodium hydroxide is the limiting reactant. So I know that all of it's going to be used up. Therefore, I'm going to have 0 moles of sodium hydroxide in the end. So, since it's a 1-to-1 molar ratio, I take away 8.75 times 10 to the minus 3 from both sides. And I get... Alright, so this is my final moles of ethanoic acid that I have left in the mixture. Now, if this was a strong acid, I would know that we have that many moles of H plus ions left as well. However, since it's a weak acid, it doesn't fully dissociate. If you want a better explanation on this, watch my video on weak acids. But essentially, to answer this, I need to use Ka. Alright, now this is my formula for the Ka expression of ethanoic acid. Now, I know that my value here is 1.7 times 10 to the minus 5 for ethanoic acid. And I know I can simplify this expression by writing H plus squared, so that I get... And now, to work out the H plus concentration, all I need is the concentration of ethanoic acid. Alright, so I got this concentration by doing the moles divided by the total volume in decimeters cubed. And I can sub that all into this expression, so that I get... And now I just need to minus log this to get the pH, which is... Alright, so that's neutralization reactions done. If you want some more practice, check out the exam questions on my Google Drive.